math part, and then Nilabha will take over the crypto part. So I'll just list out what all I'll be covering. So first we'll start with modular exponentiation. So yeah, size. So इससे पहले we'll just discuss an algorithm, repeated squaring. Let's say you have a number a and you have to calculate a power 22. So you give this to a computer. So one of the methods that the computer calculates may be a into a, so on until 22 times. So it takes 22 steps to calculate this. That may be one of the way. But instead, suppose the computer does it in this way. First it calculates a square, then it multiplies a square with a square and calculates a power 4. Then it calculates a power 4 into a power 4 and a power 8 and then 16. And for a power 16, you cannot double it, so the least you can add is, the least you can multiply is with a power 4. So a power 16 into a power 4 into again a power 2. This will give you a power 22. So the number of steps that you take to calculate a power 22 is significantly reduced when you use this method of doubling or something like that. So this is like dividing 22, writing 22 as sum of two powers. So 2 power 4 plus 2 power 2 plus 2 power 1. So we first calculated this a power 16, and then we also had the a power 4 intermediate value that we multiplied it with, and also we had a power 2 in the beginning that we multiplied it, and finally we got a power 22. So the number of steps are drastically reduced. So this is repeated squaring. Instead of multiplying 1 by 1, 1 by 1, 1 by 1, we do it in this way. So to put it formally, like not formally, so that's it. So you just keep on squaring it until it gets to just less than that, 22. So until 16 you make it, and after that you have 22 minus 16, 6 more to cover. So now again you go until 4. So now 6 minus 4, 2 more to cover, and 2 is already 2 power. So it is just dividing it into 2 power. So that is repeated squaring. This will reduce the computation time by a lot. Now we go to modular exponentiation. So exponentiation just means doing power of something, right? So you have two numbers a comma b, a power b. This is exponentiation. But there is one more word here, modular. So it is taking modulo some number, let's say n, taking modulo n. So modular exponentiation is first calculate the exponent and then take the modulo with respect to some number. That is modular exponentiation. But calculating it directly will make it is a very bad method, because let's say you have some 10 lakh, some lakh, and b is also 1 lakh. So first calculating a power b and then taking the modulo, that is a very computationally inefficient way and bad way. So instead of that, what we can do is, at each step you can find a modulo. Let's say you have to find a power 32 modulo n. Then a modulo n raised to 32. Yeah, that is there, but that won't help so much. So yeah, one more step that you can take is, when you calculate a square, again take modulo n. At each step you take modulo n. First you take a and do modulo n. Then let's say you got some number. You can take some example. Let's say you have 20 power 6 modulo 7 you have to find. So first you take 20 modulo 7. How much is it? 20 modulo 7, you get 6. Now you do 6 square. Now we are using repeated squaring method in here because we already know that it is very efficient, so use that method here. You have to calculate power 6, so first calculate power 2, you get 36. Now again you find modulo 7, 36 mod 7, you get 1. So you already did power 2, so you have to do more power 3 to get whole power 6. So 1 power 3, you get 1. So that is this 1 modulo 7, final answer. Instead of calculating 20 power 6 directly, at each step of repeated squaring, we are doing the modulo operation. And why does it work? Because of the property that a power n mod any p is equivalent to, sorry, this is same as a modulo p whole to the power n. So whenever you are doing squaring, a square mod p is same as a mod p whole square. So at every step of squaring you can take modulo and then do the squaring again and again. So in this way you can calculate modular exponentiation very quickly.
Can you directly do -1 power 6?
Sorry?
Can you directly?
Yeah, in this specific example you can do, but this may not work everywhere, right? So in general the method that works is at each step of repeated squaring method to find the exponentiation, you take the modulo and do the exponentiation instead of directly doing the exponentiation. Is it clear? So I'll discuss three theorems of number series. So first one is Fermat's theorem. So if you have a number a and a prime p such that p does not divide a, then a power p minus 1 is congruent to 1 mod p. This you would have seen in school and you would have seen this a lot of times. I'll just quickly go through the proof of this. So a power p minus 1 is congruent to 1 mod p. It always feels like to multiply on both sides or something like that, right? So just out of intuition, maybe let's try multiplying a on both sides. A power p is congruent to a mod p. Suppose we are able to prove this, then since we know that p does not divide a, take a on the left side, a into a power p minus 1 is congruent to 0. If we can prove this, then we get this, and p does not divide a. So p will divide this. So that will be proved. So proving this is same as proving this for the case of p does not divide a. So if you want to prove this, like one thought that you may get, I mean, do you have any ideas? For proving a power p is congruent to a mod p. Like one idea I'll just discuss, we don't have much time, that's right. So let's say you try to take a plus 1 whole to the power p and try to expand it. Then we get 1 plus pc1 into something plus pc2 into something, so on, pcp minus 1 into something plus a to the power p. Note that pck is always divisible by p for any k, because we will have things of the form p factorial by p minus k factorial into k factorial, and this does not contain any p, this does not contain any p, but the numerator contains p. So pck is always divisible by p for all k in the range k equal to 1 to p minus 1. So all these terms in the binomial expansion of a plus 1 power p are divisible by p. So a plus 1 power p is congruent to 1 plus a power p. These are the left out terms, 1 and a power p, mod p. So can you see which method I am going to use now? There is a plus 1, there is a minus 1. So we can use induction. So when you use induction, on the left hand side you will get a plus 1 power p. I started with a plus 1 and a, you can start with a and a minus 1. So if I start with a and a minus 1, I will get a power p on left side. On right side of the congruent symbol, you will get p minus 1, sorry, a, you will get a, because from a plus 1 to 1 you are going, right? So you will get a power p is congruent to a mod p when you use induction and sum all the things.
We're doing induction on p or induction on
Induction on a plus 1 power p, a power p, a power p, a minus 1 power p, so on. this is one method of this. You can discuss more methods in the end if you have more time. So this is Fermat's theorem, and the general thing, A for P congruent to A mod P is true for all A, irrespective of whether P divides A or P does not divide A.
Which one is always true?
A for P is congruent to A mod P. Like irrespective of P, it can be any A, but P should be prime. So next we'll discuss Euler's torsion function. So if you have a number, natural number n, phi of n is Euler's torsion function. It is defined as all the numbers less than n, all the natural numbers less than n, and co-prime to n. This is Euler's torsion function. For example, for n equals to 10, phi of n is 4. Because we have 1, 3, 5, 7. These are the only numbers which are less than 10 and co-prime to 10.
5 is not co-prime to 10.
Sorry? Oh, sorry. 1, 3, 7, 9. 1, 3, 7, 9. So these are the four numbers which are co-prime to 10 and less than 10. So this is the simple definition of phi of n. This is Euler's torsion function. So one of the applications of this is, if you have a natural number a and a number n such that GCD of a comma n is 1. So a comma n are co-prime. N can be any number, it need not be prime. A is any natural number, n is any natural number such that GCD of a comma n is 1. Then a to the power phi of n is congruent to 1 mod n. This is Euler's theorem. So for example, here you have, let's say, you take n equals to 7, sorry, a equals to 7, n equals to 10, then 7 to the power 4, phi of 10 is 4, is congruent to 1 mod 10. So we'll discuss the proof of this at the end if we have time. So now change the Mendel theorem. Let n1, n2, so on be natural numbers which are pairwise co-prime. Like each one of them is co-prime with all others. And let a be any natural number, so let x be any natural number such that x is congruent to, let's say, a1 mod n1, and x is congruent to, let's say, a2 mod n2, so on. X is congruent to ak mod nk. Here n1, n2, so on until nk are any k natural numbers with a pairwise co-prime. Each one of them is co-prime with others. Then Chinese remainder theorem tells that there will exist a solution for this. There will exist an x which satisfies all these equations. That is Chinese remainder theorem. So if suppose, let's say, there exist two solutions, there may exist any number. Let's say there exist two solutions, x1 and x2. Then Chinese remainder theorem further tells that x1 is congruent to x2 modulo capital N, where capital N is n1 into n2, so on until nk. Define capital N like this. Then if there exists any two solutions, for any two solutions, this is satisfied. So proving this is not that hard because you'll get x1 congruent to a1, x2 congruent to a1. So from there you'll get x1 is congruent to x2 mod n1. Similarly you'll get x1 is congruent to x2 mod n2. So you'll get k equations, x1 congruent to x2 mod nk, and after doing some more math you'll just find out that it is also congruent to x2 even if you multiply all those n1, n2, n3 so until nk. Because see, x1 is congruent to a1 mod n1, and since x2 is also solution, so x2 is also congruent to a1 mod n1. So x1 is congruent to x2 from these two equations. x1 is congruent to x2 mod n1. So similarly, x1 is congruent to x2 mod n2. So on until nk. Now, if x1 is congruent to x2, it means x1 minus x2 is divided by that. So n1 divides x1 minus x2. n2 divides x1 minus x2. So on. And one important thing to note that n1, n2, so on until nk are all pairwise coprime. So let's say suppose a number a divides n, b divides n, and a and b are coprime. Then a into b also divides n. Why is this true? Because if a divides n, then n by a into a, this is a natural number, and b also divides this thing. But b does not divide a, and b is coprime with a. So from the properties of coprime and all those, we know that if this is coprime to this, then this must divide the other part. So b divides n by a. This is same as ab dividing n. So from there we get that product of all these things will also divide x1 minus x2. Hence n, which is the product of all this, we get this equation x1 is congruent to x2 mod capital N. One more statement that we made was there exists at least one solution for all these equations. So why is that true? We have a lot of numbers here, n1, n2, so until nk. So instead of proving for k numbers, let's try proving it in the case of two numbers. X is congruent to a1 mod n1, x is congruent to a2 mod n2. Then so there is some construction through which we can show that at least one solution exists. So the intuition of that construction, even I don't know, but I'll just tell you the construction. So you know that whenever two numbers are co-prime, there will exist coefficients. Let's say x and y are co-prime. Sorry, let's say a and b are co-prime. Then you would have learned in school or college that there will exist coefficients x comma y such that a into x plus b into y equal to 1 if a and b are co-prime. So we know this from school, right? If GCD of a comma b is 1, then there exists x comma y such that ax plus by equals 1. So if you use that here, n1 and n2 are co-prime. So there exists coefficients m1 comma m2 such that m1 n1 plus m2 n2 equals 1. Now if you take the number a2 m1 n1 plus a1 m2 n2, so this is a construction to show that solution exists. So why is this a solution of this? You can clearly see by substituting the above thing here. You get a1 minus a2 into m2 n2 plus a2. So this if you take modulo n1, sorry, if you take modulo n2, you get it is congruent to a2. The remainder will be a2 when you take modulo n2. Similarly, if you take m1 n1 as m2 n2 as 1 minus m1 n1, you get the other thing, x is congruent to a1. So we showed that there exists at least one solution. Now by using induction, again you can extend this to the case of n1, n2, n3, so on until nk. So any doubts till now? So I'll just quickly recap what all I showed. So first we discuss the method of repeated squaring. This is very efficient for calculating exponent. Let's say if you want to calculate a to the power b, instead of multiplying b times, you can use repeated squaring to calculate it very efficiently. This was the first thing. And then we discuss what is modular exponentiation. It is just exponentiation, but at the ending you have to take modulo n. So instead of taking modulo n at the ending, you can take modulo at every step of the multiplication process. That will make it very efficient, because otherwise you would have to calculate very huge numbers and at the ending you have to take modulo. That is very inefficient. And then we discuss Fermat's theorem. A power p minus 1 is congruent to 1 mod p, where a is any number which p does not divide. So for that we saw a proof using induction. A plus 1 power p is congruent to 1 plus a power p mod p. This we proved using binomial expansion, and on this we inducted. And then Euler's torsion function. So phi of n is defined as amount of numbers, or the quantity of whatever, the number of numbers which are less than n and co-current to n. This is Euler's torsion function. For example, phi of 10 is 4, 1, 3, 7 and 9. So then we get Euler's theorem. A power phi of n is congruent to 1 modulo n. This is Euler's theorem, where a and n are any two natural numbers such that GCD of a comma n is 1. And phi of n is the Euler's torsion function. For example, 7 power 4 is congruent to 1 mod 10. So why are we even discussing all this? Like maybe in cryptography, let's say you want to calculate some a power b, some huge thing, modulo some number. Then in the process of that, you can use all these techniques. You can use repeated squaring, you can use modular exponentiation, you can use Euler's theorem, such as maybe somehow you found that a and this n are co-prime. So if you know phi of n somehow, then maybe you can reduce this problem. So all these things that we discussed, are like they may be useful. So and then Cheney's remainder theorem. If you have, so I just discussed it right now, so I won't repeat it. Next. So what is discrete logarithm? So exponentiation means, let's say I've given you two numbers a comma b and I asked you to find a power b. This is exponentiation, right? So discrete logarithm is kind of the opposite. Let's say I give you the value of b power k. I give you that b power k is congruent to, so let's not go to modulo first, let's stick to basics. Let's say I've given you the value of b power k and I give you the value of b. I give you value of b and of b power k also, and I asked you to find the value of k. So what will you do? You'll just take simply logarithm. You take log of b power k to the base b. So this is a simple problem. You can solve it quickly and efficiently using a computer. But let's say if you go to modular exponentiation, I have given you that b power k is congruent to c modulo some number m. This is the equation that I have given you. You know the value of n, you know the value of b power k, you know the value of c. I have asked you to find the value of k. For example, I can tell you 81 or 3 power k is congruent to 13 mod or any random thing, let's say 3 power k is mod 20 or something, let's say. So this is the equation and you need to find the value of k. So is it so easy as finding logarithm or something like that? It's kind of difficult because in when you're taking modulo, it won't be an increasing function or maybe some decreasing function, it won't be. It will just randomly oscillate. For example, if you take 3 power k as a function and you're changing the values of k, let's say modulo 4. So at 3 power 1, it will be 3 power 1 is congruent to 3 mod 4. So 4 is a very small number, let's say 12, 11. So 3 power 1 is congruent to 3 mod 11. Whereas 3 power 2 is congruent to 9. Until now it's increasing. 3 power 3 is congruent to 5 modulo 11. 3 power 4 is congruent to 4. So is this random, like initially it was 3, then 9, then 5, then 4. 3 power 5 to 43, you will get congruent to 1. So is this a random sequence of numbers when you keep on increasing the value of k? So with computer, but let's say you don't have module 11, then if I give you that 3 power k is 243, you can just use like what is that thing? Binary. What is the word? Binary search. You can just use binary search to find it. Like let's say between 1 and 10, between k equal to 1 and 10, you do binary search to find the value of k such that 3 power k is 243. So you can just quickly calculate in the case when there is no modulo. But when there is modulo, things get very complicated because the sequence of values that you are getting when you are increasing k, they are just random. It's not so easy to predict. So if you are given this equation b power k is congruent to c modulo n, you are given c, you are given n, you are given b power k, it's not so easy to find the value of k. So that makes this problem very hard. So like hard in terms of what? That you will learn later. It's defined in terms of complexity classes. NP hard, P hard, you'll learn later. So,
Will also be given B, right?
sorry?
Will also be given B.
Yeah, also B. You just have to find k. So this is a very hard problem. So this being hard will make it useful in cryptography, like when encrypting and all. Because let's say if k is the key, it's not so easy to find the value of k when you are given other things. So you can use this somehow in cryptography. The fact that this is very hard. Since this is hard, it is a bit like you cannot decrypt this, you cannot find the value so easily. So that was with discrete logarithm. I'll just discuss some basic terminology in group theory. Like what is group theory, what are groups. So I'll define first what a group is, then you may get some intuition. Group is just a set of numbers. Think of it like a set of numbers. Sorry, not a number, not numbers. Set of elements. Think of a group as set of elements G which satisfy some properties. So first thing, binary operation. For example, addition is a binary operation. If I give 3, if I give 5, so addition is a binary operation that takes 2 inputs and gives an output. 3 plus 5, 8. So similarly, multiplication, they are also binary operations. They take 2 inputs and give 1 output. So a group G also has a binary operation. If you take some element, so what exactly do I mean by element? It is discrete, like don't think of, think of it a bit rigorously. So let's say G1 is some element, G2 is some element, it may be a number, it may be a matrix, it may be anything. And define an operation between these two, G1 star G2. For example, 3 plus 5, G1 is 3, G2 is 5, star is plus. This is an example. Or maybe G1 is some matrix, G2 is some matrix, and star is minus. So you can there can be different interpretations for this. So G1 star G2 equals G3, where G3 is also an element of this set G. So first thing is binary operation. Take any element of the set G, take any other element of the set G, and perform a binary operation between these two. This binary operation is fixed. Let this is star for this group. This is fixed for this group. Then it should produce an output G3, which also must belong to the group G. So this is closure property of binary operation. So you know what closure is, right? We were taught in school like the output should also belong to the same class. For example, like whole numbers are not closed under subtraction, but they are closed under addition. So the group should be closed under the binary operation star. That is one property. Second property is that there should exist some element. So this you think of it just as a set of elements. Set of elements, they can be numbers, they can be anything, they can be matrices and all. There should exist some element in the set of elements. I will call it identity E. I am just naming that element as identity. That element satisfies the property that E star G equals G star E equals G for all G in the set of elements capital G. For example, if you think the set of elements as let's say natural numbers, sorry, whole numbers, and let star be defined as plus, then in that case identity E will be the element 0 in whole numbers, because 0 plus any number equals that number plus 0 equals that number itself. So I am just giving an example of what this is, 0 plus n plus 0. So there must exist an element in this set, that's called the identity, that satisfies this property. So these two properties it should satisfy, and there are two more properties that it needs to satisfy for it to be called a group. The third property that this set should satisfy is associativity. Associativity of the binary operation. So A star B whole star C must be equal to A star B star C. So this must be satisfied for all A comma B comma C in that set G. So this is one more property that it should satisfy for it to be called a group. And the last property is inverse must exist for every element. So what does inverse mean here? So inverse means that G dash is inverse of G. G dash is an element. G dash is an element in the set. G is an element in the set. G dash is called inverse of G if G dash star G equals G star G dash equals identity E, which we defined in the second property. So for every element G, there must exist an element G dash in the set such that this is satisfied. And inverse of G dash must be unique. Inverse of any element must be unique. So inverse of G dash is G and inverse of G is G dash. Because if you interchange them here, it will satisfy. So inverse must exist and it should be unique. So these are the four properties that a set of elements should satisfy. If it satisfies, then it is called a group. For example, take the set of elements 0, 1, 2, so on until infinity, the set of whole numbers, and define the binary operation star as plus. Sorry, take the set of integers. Take the set of integers and define the binary operation as plus. Then we'll check whether these properties are there for that set or not. First property, binary operation. Take any two elements in this, do the binary operation, that must belong to the set. It does belong, right? So closure, binary operations, closure property is satisfied. Second property, identity should exist. 0 belongs to the set, and for any number if you add it to 0, you get the same number again. So identity does belong to the set. So second property also satisfied. Third property, associativity of binary operation. We clearly know that addition is associative. So third property is also satisfied. Fourth property, inverse must exist for all elements in this set. Take any element of the set, let's say any number n. Clearly minus n belongs to this set of integers, right? So inverse does indeed exist for every element in this set. So fourth property is also satisfied. So since all these four properties are satisfied, this set of elements, which is Z, under the operation plus, this is a group. So when you're defining a group, you need to give a set of elements and a binary operation for that set of elements. One more example can be matrices of 2 into 2 order, which are invertible. Matrices which are invertible, A, B, C, D, where A, B, C, D belongs to real numbers, let's say, and determinant not equal to 0. So if you take the set of all such things, where A, B, C, D belongs to R and data is not equal to 0, if you take the set of all such matrices, and let's say you define the binary operation star as matrix multiplication. Then that is also a group. You can check that all the four properties are satisfied for even this set also. So group is just an it's just abstract thing. You can give it multiple So is there any doubt in the definition of group? So this thing you see, this is the definition of group. That's it, and nothing else. Now, if I ask you now, what do you think a subgroup might be?
Subset of group.
Yeah, subset of group. But it says subgroup. So that subset should also be a group in itself. That should satisfy the group properties. So a subgroup, let's say H is a set of elements, such that H is subset of the set of elements G, where G forms a group under binary operation star. Okay, G is a set of elements under binary operation star, and H is a set of elements which is subset of G. Then H is called a subgroup of G if H is closed under star. H is closed under star. I'll tell what is this, and H should satisfy group properties. Then H is called a subgroup of G. So H is closed under star. By this I mean, if let's say two elements H1, H2 belong to H, so they also belong to G because H is a subset of G. Then H1 star H2 will be obviously defined because we define star for all elements of G. So let's say this is some element G. Then this G must belong to H. That's what it means by closed. Only then you can multiply any two things within H and get something again back in H, right? Else, if this doesn't happen, then you take some two numbers in H and suddenly it's going out of H. Then that won't be a group, right? That has no meaning. So H should be closed under binary operation star, and also H should satisfy all the group properties that we discussed in the previous page. Then H is called a subgroup of G. Now we discuss cyclic group. So till now we just saw binary operation between two different elements. Let's say if you do binary operation between a same element A star A, this can mean anything. It can be A plus A if star is plus. It can be A into A, etc. So this you just write it down as A box square, let's say, or let's just say A square. So here A square doesn't mean A multiplied by A. It just means A star A. For example, if star is plus, then A square means 2A. Because that will become A plus A, right, in that case. So A star A will become 3A if star is plus. It will become A raised to the power 3 if star is multiplication. So depending on interpretation that you give to star, A square. So here A square does not mean that star is multiplication. I am just telling that A square means A star A. That is the definition. Okay. Then if you take the set of elements A square, A cube, so on, where A power n means A star, A so on, n times. Then, and also you take this A power minus 1, A power minus 2, so on. What does A power minus 1 mean then? A power minus 1 means take the inverse of A whole power 1. A power minus 2 means inverse of A power 2. What is inverse of A? We know that for every element A in the group there exists an inverse of that element, right? So that is this element. So this is how A power minus 1, A power minus 2 so on are defined. If you take this set, then note that any two elements you multiply within this set, it again belongs to that set only. You take some element A power m, you take some element A power minus n belonging to this set, multiply both of them, it will mean A power m minus n. Why is that so? You can just try it out yourself. For example, A star A power minus 1. So this is A square into A power minus 1. So this means A star inverse of A, right? And we know by associative property that this is equivalent to A star inverse of A. I'm just changing the order by using associative property. And A star inverse of A is identity E from the properties of group. I'm just using the properties of group and nothing else. So then we get A star E here, from here. And A star E is A, again from the properties of group. So A square into A power minus 1, we got A by using associative property and other properties of group. So similarly, A power m into A power minus n, you'll get A power m minus n using the properties of group. And this clearly belongs to this set, right? Because that's, you can see clearly A square, A cube, A power minus 1, A power minus 2. So A power m minus n also belongs to this set. So you can prove that this set is a group. Like it satisfies the properties of a group. The 4 properties that we defined on the first page. This set of elements satisfies those properties. So this is a group and it is a cyclic group. So a cyclic group is a group which is generated by a, if it can be generated by an element. So generated means this thing only, like A square, A cube, so on, A power minus 1, A power minus 2, so on. This means this is generated by the element A. That's what generated means. So if any group can be generated by a single element, then that group is called cyclic. Then that group is cyclic. So clearly it is generated by A, so it is a cyclic group. And cyclic subgroup means it is a subgroup and it is also cyclic. So sir?
For subgroup and main group, the main element should be same, right? There. Like,
Main element as in identity.
Like if it's it's generated by, if main group is generated by A, then subgroup should be generated by A, right?
No. If subgroup is generated by and main group is generated by, then both of them are equal, right? One will not be the subgroup of other. So maybe subgroup is generated by A square or A power k. For example, main group is 1 A square, so on, A power minus 1, A power minus 2, so on. The subgroup of that can be 1 A cube, A power 6, so on. A power minus 3, A power minus 6, A power minus 9, so on. All these are subset of original and is also a group. So we discussed group, subgroup, and what is the meaning of cyclic in groups. So one last thing, I'll discuss what are primitive roots. So this is, let's say this is not related to group theory, like just leave that group thing part, this is separate, let's say. So this is just a simple definition. A number G, okay, let's say a number M, okay, is called a primitive root. It's called primitive root modulo M. If So this is just a name. Primitive root modulo name is just a name. If for any number a such that GCD of a comma n is 1. For any number a such that GCD of a comma n is 1, there exists k such that m power k is congruent to a mod n. So any number, let's say you are given some number, natural number n. Let's, for example, 81. Okay, and you are given. If you are given 81, then a number is called primitive root modulo 81 if for any number a that you choose such that a and 81 are congruent to each other, you will always be able to find a k such that m power k is congruent to a model. Okay, like let's say if I take m equals 5, then and I take any a, let's say I take a is 7, clearly GCD of 7 and 81 is 1. So if I am able to find a k such that 5 power k is congruent to 7 mod 81, if I am able to find such a k for any value of a, if I am able to find such a k where a is such that GCD of a comma n is 1, then such a number m is called a primitive root modulo n. So if you, let's say, try to generate from it, generate as in just as the previous page we saw. So if you take m square, n cube, so on, and m power minus 1, m power minus 2, so on. Clearly, this should contain all those a such that which are GCD of a comma n is 1, right? Because you are able to get an k such that m power k is congruent to a model for any value of k. So in this there will be some k such that m power k, there will be somewhere m power k will be somewhere such that this thing is congruent to a model of n. So if you take this generated group m square, n cube, so on, m power minus 1, m power minus 2, so on. This
It will also include 1, right?
Sorry?
It will also include 1, right?
Yeah, 1 also. So if you take the set of these elements, this is just a set of natural numbers like 5 square, 5 cube, so on. Okay? Sorry, ignore m power minus 1, m power minus 2.
It would be 1 or e.
Sorry?
It would be 1 or e.
1 or e. No, this is not a group. For now, we are just discussing natural numbers.
Okay, nice.
You can define this for groups also, but for now, let's say natural numbers. So if you take the set of all these elements, this should contain all a when you do modulo n. If you do this set modulo n for each of the elements, this should contain all a such that GCD of a comma n is 1. Do you agree? Because for that for any a, you will have some m power k, and that some m power k will definitely be present in this. So this is a very useful property that this set of elements contains all the numbers which are congruent to n, and all these numbers which are congruent to n, this we saw in another place also, like Euler's Taussian function, if you remember. So yeah, primitive. This is the definition of a primitive root. Now Nilabha will just take over.
Could you just repeat this example?
Yeah.
Can you give a smaller example where, say for n equal to 3, you can show a primitive root?
So let's say you have n equal to 3. So look, 3 is small. Let's say n equal to 7. So what are the numbers which are less than 7 and co-prime to 7?
All.
All, because 7 is a prime number. So for each of these numbers, when you put a equal to 1, a equal to 2, so until a equal to 6, in all the cases you should be able to find a k. You should be able to find a k. So let's say m is 5. 5 or k is congruent to a mod 7. Sorry, mod 7. If I substitute a equal to 1, a equal to 2, a equal to so on until a equal to 6, In each of those cases, I need to have a solution for k. If I have a solution for k for each value of a here, then phi will be called a primitive root. So for which all values of a, for all those values of a which are co-parent to this number, if I substitute all those values of a which are co-parent to n here, in all those cases I need to find a solution. I need to be able to find a solution for k. If that happens, then phi is called a primitive root. Okay.
K belongs to integer.
Yeah, k belongs to natural numbers. Like this is only in the case of natural numbers. Here instead of phi, you can have an element g belonging to a group. K still belongs to natural numbers, where g power k is defined as g star g, just as how we define for groups. And instead of congruent to, you can keep equal to some element a which also belongs to the group. Let's say g dash.
How do you define co-prime here?
In groups?
Yeah.
No. That modular example gave it. For groups, you just keep equal to.
Okay.
So, yeah.
Okay, thanks Chidvilas for taking care of
You want to take the mic?
Yeah. So can
you give him the
have
mic?
Okay, sorry.
Oh, there is a mic. Okay. Thank you. I'll just keep my phone here. So open my box. Okay, am I audible? Is everyone able to hear me? Great, okay. So today we will try to come back to the problem I outlined the last time. Let me just put it in here for convenience. Which is the one of the biggest, okay. Which was, yeah, this screen was never on.
Wait, let me.
So can you turn it on is the question. No, this isn't on. Was this on before? No, right?
I can check it.
Let me write something.
Right or left? I should do left.
Is that connection
Check.
Nothing is coming up, right? Or is something
Can you try over there? Put that down.
No, I don't think to outside anything is coming up. It's not mirroring, right? So there are some black squiggles here, so they should come up there.
So just ignore this one. It's fine. It's fine, right? You guys can see from that board. Yeah.
Is this move up? This isn't movable. Yeah, so if any of you that want to shift a little, feel free to do so. Otherwise, yeah, you can leave it. Okay, yeah. So the problem, which was a problem a few years back, it's actually a few decades back at this point, that is, I have two nodes connected to each other by public network. These two nodes, quote unquote, can identify each other by say each of these nodes. By nodes I mean their computers or servers. Each of these nodes can identify each other because they have a unique ID, and for now we'll assume that the ID can't be forged. But these two nodes have never spoken to each other before, and their only way of speaking to each other is through a public channel. So how can they, quote unquote, have a conversation with each other such that only they understand what's going on in the conversation, but no one else does? So, one thing we figured out last time is if we can encrypt data. So if, say Alice wants to talk to Bob, if Alice can encrypt her data and send it to Bob and Bob can decrypt it, we have solved the issue. But this leads to another issue, that is, for them to do this, Alice and Bob need to have a key. And since they've never spoken to each other before, how do they get a key across, right? So you can say, Alice just sends the key over to Bob, but the only way for Alice to send anything to Bob is over the public network. And if she's sending the key to Bob, then the public network can read the key. So basically, whatever Bob can do, this public network can do. And this sounds a little challenging, right? I mean, Bob has the exact same amount of information as Alice does in the network. Sorry, as the public network does. So how can you quote unquote distinguish between Bob and any other person in the network? And that's the first part. So you kind of need an asymmetry. You need Bob to know something the rest of the network does not. You need Alice to know something the rest of the network does not. And Alice and Bob somehow need to concoct their, privately known some things together to communicate with each other. But how exactly do we achieve that? So this is where all the maths you just looked at will come in handy. So this is one problem I want you to take as hard computationally. So given your, so assume that you are given two large primes, p comma q. So these are large primes. And so assume p and q are two large primes, and I take their product. So a product of two primes is called a semi-prime. So n is a semi-prime. So given a semi-prime whose prime factors are large, turns out it's very hard to factor it. So if I just give you n, I don't give you p and q, if I just give you n, turns out it's a computationally hard problem to factor n. And we are going to build a crypto system which can achieve, what we want under this assumption. So the question is, what is the validity of this assumption? So turns out you need to be careful. So for certain bad values of p and q, this n is actually very easy to factor. But if you quote unquote choose p and q well, in a certain sense, which I will not go into, but if you choose them well enough, then it turns out that n is a difficult problem to factor. It's not a mathematical theory that n is computationally hard to factor. We don't really know that. It's a hardness assumption of sorts, and no one has been able to mathematically prove or disprove the fact that it is computationally hard. It's just that we have tried for centuries to come up with an efficient algorithm for factoring, and we haven't been able to. So people just believe that it's hard to factor. So here is what we are going to do now. So this is what I'm going to cover now is called the RSA crypto system, and this stands for Revised, Agelman and Shamir, the three people who worked on this. And how many of you have heard of CLRS? Okay, computer science and half computer science, half math folks have. So the R in CLRS stands for Ronald Rivest, right? It's the same R here. And I forgot if the S is the same as this. Is it Shamir in CLRS? It's not Shamir, right? Yeah. Anyway, the R is the same, that I know. Anyway, so here is how the RSA token called public key crypto, it's called public key crypto system. So before we dive into it, here is the pop culture idea of what works. So what Alice is going to do is that what Bob is going to do rather is that Bob is going to generate two keys, a public key and a private key. Okay, so somehow this public key and private key are related to each other with the following property, that any message encrypted with the public key can be decrypted only with the private key. And how do you achieve this magical property? We'll get to, but assume that you have this magical property where any message encrypted with the public key can only be decrypted with the private key. This is why this is called asymmetric key cryptography, as opposed to our previous notions which had symmetric key cryptography. The reason they were called symmetric keys because we use the same key to both encrypt and decrypt. Though over here in this setting, the encryption and decryption key are different. So now what Bob does is he keeps the private key strictly to himself and makes the public key available to everyone. So now it's simple for Alice to send a hidden message to Bob, right? So Alice just encrypts her message using the public key and sends it over to Bob. And since only Bob has the private key, only Bob can decrypt and read the message. So we have given some kind of pop culture to the magic, but we still haven't explained how the magic works, and that's what we're going to do with the math now. So what does Bob do? So first it needs to generate it. It needs to generate it. So Bob is going to sample two large primes. Yeah. And he's going to sample it well so that they're secure large primes in a sense. He will compute n is equals to p into q. Yeah. Then he will take a public constant called e, which for now you can think of as like 65537. You can take it to be some other values also, but in practice e is taken to be 65537. And there's a reason for doing that. So if you take, I'll come to what the issue is, other values of e could be. And what he does is that he makes publish e comma n. This is the public key. This is the public key for Bob, just e comma n. Now he does some other magic too, okay, no, I'll come to that magic later. And the private key is this key comma q. It's in practice he actually stores something else for efficiency purposes, but for our purpose, having key comma q. So essentially, if I'm doing this, I'll also have to put e. He needs to remember e too. Yeah. So the thing is, the difference between the public and the private key is, in the private key we have the factorization of n, but in the public key we don't know the factorization, and this will cause all the difference. So here's how it goes. So how does Alice encrypt something? Okay. First of all, Alice takes a message n. So you take any message, you can represent it as in binary, and you convert that binary to an integer, right? So the first constraint you need that message m should be less than capital N. So since p and q are large primes, n will also be like a large number. So usually you take p and q to be 1024 bit primes, then n is 2048 bits. So you can fit like a sentence worth of messages in that easily. Of course, if you want to send many messages, you can just encrypt many messages sequentially. So we need this m less than n over there.
Using the same encryption scheme for all the messages is not vulnerable.
It's not a good idea.
It's not.
No, the same encryption scheme is fine, but you should be using different private public keys.
Oh.
Because if I send the same message block twice, the ciphertext will be the same. So that leaks information on the fact that my message is the same. But yeah, ideally, if you really want to communicate in real life, you're not going to use a public key crypto system, so this won't be navigated. This will be navigated, and we'll come to it in a bit. What will you do instead? For now, just assume you have to send exactly one message. So now what Alice is going to do is that she's going to compute m to the power e mod n. This she can compute, right? She knows n, she knows e, and this is her ciphertext. And Alice is just going to send C to Bob now. Now the question is, okay, how will Bob recover M, right? So this is what Bob does. So Bob has C now. So Bob computes the following. So he computes D inverse, sorry, D is E inverse mod phi of n. Right, phi of n is the order distribution function. So first of all, what is phi of n? Phi of n is phi of p times q, right? Which is prime. So can anyone tell me what this will be?
P minus 1 times.
This is p minus 1 times q minus 1. Which Bob can easily compute, right? Because Bob knows p and q. So can compute phi of n.
And you say why this will be p minus 1 times q minus 1?
That's the math we just did. This is the formula for order distribution.
I mean, I don't think we covered the formula
Did we not? Okay.
with the prime factorization.
So, okay, so say you have, you want to calculate the value of p1 to the alpha 1 beta. Pn to the alpha n, where these are all distinct primes. Okay, so this is nothing but P1 to the alpha 1 product Pn to the alpha n times 1 minus 1 by P1 times 1 minus 1 by P2 dot dot 1 minus 1 by Pn. So if you bash this into phi of PQ, this will be PQ 1 minus 1 by P 1 minus 1 by Q equals to PQ into P minus 1 into Q minus 1 by P by Q into P into cancels out, you get P minus 1 into P minus 1. Yeah. Okay. So phi can be easily calculated. So given that phi can be easily calculated, it's easy to take the inverse. So Bob can have dt. Now what Bob is going to do is he's going to take the ciphertext, raise that to the power d, and then take mod n. And the surprising result is that this will be equal to the original message. And we now need to prove this, right? We need to prove that this is indeed the case. And why is this the case? Let's see. So this is the case because if you look at c to the power d, that is nothing but m to the power e to the power d, right? Which is m to the power ed. Now ed is congruent to 1 mod phi of n, right? Because d was e inverse mod phi n. So that means that ed is some k times phi of n plus 1. So this is m times k times phi of n plus 1, which is nothing but m into m to the phi of n mod k to the power k. And remember, we are doing all of this mod n. Mod n. Yeah. So m to the phi of n mod n is, by Euler's theorem, 1. So 1 to the power k is 1, and we get n here. So decryption works correctly. So what can an attacker do? So attacker has m to the power e. So you know, if the attacker can factor n, he can clearly like decrypt on his own then. So that's why you need the difficulty of the factoring. Alternatively, he could essentially, what you're doing is taking the eth root in a sense, right? So the problem with taking certain small exponents is that over integers it's easy to take e roots. So if e is 2, taking square roots is very easy. Even over modern, taking square roots is a little easier than other powers of e. And for e equal to 3, if like n is large enough such that m cubed is less than n, then again you can just take an integer cube root, which is easy. Turns out if like n is not too large so that m cubed is actually significantly greater than n, then taking cube roots is difficult, but then these things are vulnerable to other kinds of attacks which will come to. But does everyone see how RSA works? And you can see how like Alice and Bob need not have ever communicated before, yet they are able to quote-unquote securely communicate with each other through a public network.
But and how is that private key only with Bob? So
Bob needs to keep it to himself. So Bob generates the public-private key pair and keeps the private key to himself. So if he leaks the private key, anyone who has Bob's private key can read his messages. So Bob needs to store his private key. And in fact, if you read these, if you go into this Web3 field and you read about Bitcoin and stuff, they'll always tell you keep your private key to yourself. If you lose your private key, you lose all your Bitcoins. This is exactly the reason. This is not exactly the reason. Basically, if you lose your private key, anyone can sign things on your transactions on your name. But this is where it branches from, that you keep the private key strictly to yourself.
What was Reddy's question I forgot? Reddy's question function.
What is function? So Euler distribution function of n is basically the number of co-prime integers less than equal to n. Yeah. And it turns out that it has this beautiful property that you can calculate its exact value using this formula. Of course, the prime zero distinctly, like pi is not equal to pj. If not, that doesn't. Anyway, so that is how I say. But now here's the question. So yeah, we have this restriction that n is less than n, right? Now I want to find a gigabyte worth of file. Gigabyte big long file. I can't send it via RSA. And in fact, the other problem is, symmetric key primitives like AES and stream ciphers and whatever, they are very fast. You have like literally hardware chips which execute them at this point. And in fact, if you look at the ASICs for, they are used for blockchain mining. They literally compute certain hash functions. They have like specialized hardware just to compute these hash functions. So the symmetric key side of things is very fast, whereas public key primitives are relatively much slower. So the thing is there any way for us to combine both worlds? So ideally, if I am communicating with you, I would want us to use a symmetric key primitive because it's faster. And like I can send arbitrarily long, I can encrypt arbitrarily long messages and you can decrypt arbitrarily long messages. We are not bound by this restriction on the message size. But then we come to the issue, how do you and I have the same key? So here's the solution, and this is called the hybrid mode. What we are going to do is that, say I want to talk to you. You're going to create a private public key pair. You're going to send me the public key. I will take this symmetric key. I will encrypt that symmetric key using your public key, send that over to you. You will decrypt it, and you will again have the same symmetric key as me. And now we can use this. Now essentially we have solved the key exchange problem in a sense, right? Both you and I have the same symmetric key. And now we can use symmetric key primitives to communicate. So our whole issue with the previous thing was that, we have good encryption schemes, but how do you and I have the exact same key when we have never talked before? So just use a public key primitive to send the key over. And you're done. And there's actually another way of doing it. So say all I want to do is literally just key exchange. I don't want to get into all of this. So the benefit of encryption is that there's a particular message I send to you. So maybe I don't care about this. In general, I don't care about the key. The key can be a random string and I'm fine with it. It's just that you and I need to have the same key. So is there a quote unquote different way of doing this key exchange such that you and I end up having the exact same key? And I don't need to control the key, but you and I need to end up having the exact same key. But because the whole thing with private public key pair is, I need to generate it, we need to use it once, it's an expensive procedure. You have a more inexpensive procedure. And that comes up through via something called the Diffie-Hellman key exchange. So this is called DHKD. And this is going to use groups. So say we are in a large group, Z by NZ, which is, so we are in a subgroup of Z by NZ generated by some element G. Yeah. In particular, what we want is that the cardinality of this subgroup is also large. Because we don't want to, this is to prevent something called a brute force attack.
Can you just mention what you mean by Z by NZ?
Z by NZ is basically the integers modulo n.
Okay.
Yeah. So, what is this? This is basically like 1 g squared g cubed dot dot is some g to the power, say, small n minus 1. Maybe g to the power n is small n equal to 1. Whatever. So we want that small n is large. Yeah. Okay, so let me call this capital N then. Okay. Now here is what Alice and Bob will do. So I have Alice here, I have Bob here. Alice is going to sample a random exponent a from 1 to n, and she is going to compute a is g to the power a mod n. Okay. And Bob is going to do the same thing. So Bob is also going to sample like a random exponent and calculate g to the power b model. Okay. And they're going to keep a and b to themselves, but what they're going to do is they're going to send capital A and capital B to each other. Okay. Now Alice is going to compute b to the power small a mod n, and Bob is going to compute a to the power small b mod n. Okay. Let's call this SA, let's call this SB. It turns out that SA will be equal to SB. Can everyone see why? Let's look at SA. SA is B, capital B is g to the power small b, this whole to the power A, which is nothing but g to the power BA, which by commutative is g to the power AB mod n. And over here, SB is A, capital A, which is g to the power small a, whole to the power B, which is nothing but g to the power AB mod n. So SA is equals to SB. And this is going to be the quote unquote symmetric key now. Another thing is, okay, what can an eavesdropper read? An eavesdropper can read A and eavesdropper can read capital A and capital B. So eavesdropper can read g to the power A and g to the power B. But the thing is, can they compute g to the power AB from it? So one way is, if you can recover what small b is, you can just raise it to the power. But turns out, recovering small b from g to the power b, that's a discrete logarithm, right? That is a hard problem. That is another example of a hard problem. So if you take appropriate groups with appropriate sizes, turns out this is a hard problem.
Does G need to be a primitive root?
Not necessarily. So that is why I take the subgroup generated by G. But the cardinality of that subgroup should be large. And of course there's certain additional security criterion, but the whole idea is assuming that discrete logarithm is hard, an attacker won't be able to recover B and won't be able to compute g to the power AB, which is their shared secret. So now you can take the shared secret and either use it directly as the key, or you can do a little bit of post-processing to make it look like a key and whatever. So this is called the differential key exchange. And okay, one more thing I do want to talk about is something called, there are two more things I want to talk about. One is digital signatures, and the other is some attacks on RSA. So okay, what is a digital signature? So you would have heard of digital signatures everywhere. So if you do blockchains, you'll hear digitally signed by the transactor, etc. It's digitally signed by the owner. If you look into your Aadhaar card, it says digital signature, and bank clients tend to make a comedy out of what digital signature it means, because they don't know what it is and they say a lot of things. And I mean, all of this is so digital signature. Okay, so here is the issue with the digital signature. So if your physical signature is there on a piece of paper, we say that you agreed to whatever contract you signed it on, right? And we do that because the physical signature is quote unquote hard to forge. We believe that. But if like say this is your signature, don't ask me whose name this is, I myself don't know. If this is a signature, you can't just take a photo of this and put it on a digital document and claim that this has been signed by me, because I can literally take that document your signature is on, crop out your signature image and put it in any document I want. I can say this guy's giving me $100 and just put that signature over there. So clearly this doesn't work. So now you can say, okay, I'm gonna have a fixed byte string, and that's gonna be the signature. But that also does not work, because I can copy paste your byte string wherever. So in fact, your signature on a document needs to be a function both of your identity and of the document, right? And such that if I do not, if I'm not you, I should not be able to quote unquote forge your signature on the document. In addition, I also need that given a signature on a document and your identity, I should be able to verify it efficiently that it is indeed signed by you, right? So how do we do that? So that is using a method called digital signatures. So digital signatures allows you to do is that, again, there are various ways to implement digital signatures. So I'll cover the naive way. So again, imagine you have a public private key pair. Okay, and say you take your message and you quote unquote use your private key on your message. Remember, previously we used to encrypt a message using the other person's public key, but what you're doing now is you're using the private key on your message to get some output, and you call that output the signature. So now, how can I verify that this was done, this was signed by you? So I use the public key on your signature, and I see if I get back the same message as what you claim it to be. Right? If that works, then I know it was done by you because only you have the private key. So the whole idea is that this is your message N. Yeah. What you're going to do is you're going to encrypt with your private key. You're going to apply the private key on your message, and you will generate some signature. And then when you see, if this is the guy who wants to verify it, he has your message, he has your signature. So what they will do is, they will use the public key on your signature and check if it is equal to your message. If they are equal, that means the private key was applied on the message, and only you have the private key. So only you could have signed it. You didn't get that? So that is one way of converting a publicly declared system to a digital signature. And so you can do it using RSA, right? So in RSA, instead of raising something to the power, instead of raising your message to the power E, you can raise your message to the power D. And only you can compute D because only you have the factors. And all I need to do to verify that a signature is valid is raise the signature to the power E and check if I get the message back. If I do get the message back, that means, it was the message raised to the power D, and only you could have done it since only you know D. So that's a digital signature. And here is one issue though. That is, say I have a 1 GB file. Okay, and I want to put my digital signature on it. So if I quote unquote, first of all, I can't use RSA because 1 GB is going to be much larger than N. And second of all, even if I didn't have bounds, my signature would also be 1 GB long, which is like bad, or like at least 1 GB long, which is bad, right? So what we do is we usually don't want to sign the whole message itself. We sign something which is instead the hash of the message. So you have something called cryptographic hash function. So these hash functions do is they take cryptographic hash function basically take messages of arbitrary length and compress them down to a fixed length output. So say n is 256, let's just say. So SHA-256 is an example of a hash function which takes any input and compresses it to 256 output, such that given the output, it should be hard for you to find an inverse image. Yeah. So the forward is easy to compute. So given an input, you can efficiently compute the output. But given an output, turns out it should be difficult for you to convert the inverse, compute the inverse image, given a random output. In fact, SHA-256, for instance, is collision resistant, in the sense that it is computationally hard to find like two inputs which map to the same output. In fact, no. So for some reason, you see any hash function will have collisions because the input is infinite and the domain is finite. So collisions are unavoidable. But there's a difference between mathematical collision existing and you being able to computationally find a collision. So in terms of SHA-256 is collision resistance in the sense that it's very difficult to find two inputs that map to the same output. In particular, so far for SHA-256, no one has been able to find out two inputs which lead to the same output. And you might think you can reverse engineer the function and all of that, but turns out that's very difficult to. And
If it wasn't collision resistant, what would be the issue?
The issue is two messages could literally, hash to the same output. So, if I sign my hash, I can later change to the other message and say, my original message was something else.
Okay.
So we need collision resistance. So yeah, so what you do in a digital signature is instead of hashing the whole message, so instead of signing the whole message, you take a hash of that message. So the hash of the message will be small, right? In particular, SHA-256 it will always be 256 bits, and you sign that hash. And if a verifier wants to verify, they'll also hash your message and then check if the signature gives you is verifies as that of the hashed message. And this is why you need collision resistance, because if I had two messages m and m prime which hash to the same value, then I can sign on m prime and then later claim I signed on m, and I can fool you. So that collision resistance is important because of that. Finally, we now come to the last leg, and this is where I want you all to participate because I know the solutions to this. There's no point. So we want to attack RSA. Okay, we want to attack some stupid variants of RSA. And these are stupid, these are insecure, but these have actually been used in practice and attacked and broken multiple times. So you get to be in the attacker's shoes now. So say I do this, okay? So I'm generating primes. I want people to send messages to me, but I get lazy. Okay, I think why generate so many primes? I just generate 3 primes and this. Right. So these are different moduli, but one of the primes is common. And say now someone sends me 2 ciphertexts. Okay. So I can decrypt and read what the messages are, but what can eavesdropper do? An eavesdropper knows, what does an eavesdropper know? Eavesdropper knows N1 because that's public information. Eavesdropper knows N2, that's public. Knows E because that's public. And knows C1 and C2 because they have been eavesdropping on the channel. Is there any way for the eavesdropper to figure out the original messages? In this case. Can anyone tell me what to do here? And you might have to use some of the maths from last week.
I guess we would get P by doing modulus by N2, N1 modulus.
So you're saying N1 mod N2 will give you P?
No, C1.
Anyone? So what's nice about P in both N1 and N2? Mathematically, what can you say about P with respect to N1 and N2? Yeah. So you can just take the GCD of N1 and N2 and that will be P, right? And taking GCD is easy. So you have Euclid's algorithm. So taking GCD is very easy. GCD is not a hard problem. So what an attacker can do is that they just take GCD of N1 and N2 and that gives P. Once you have P, N1 by P will give you Q1, N2 by P will give you Q2, and then you have the prime factors, you can decrypt the whole thing. This works. This might seem dumb, like why would someone do this? Clearly they don't know much crypto and they can do this. But turns out there was this attack a few years back where the prime number generation which they used was sufficiently biased to the point that after millions of public-private key generations, you could find moduli which were not co-prime to each other. And if the moduli are not co-prime to each other, you can break the whole security, right? This happened. And all this happened because they used a biased random number generator and stuff, like a good high entropy random number generator. This doesn't actually happen. So
for the system to be secure, all the millions and billions of prime number pairs it generates, they need to be
distinct. Yeah. So if you take say 2048-bit primes for instance, you can generate millions and billions, and if your distribution is truly random, they would be distinct with extremely high probability. And the issue with what they did was that it wasn't truly random, and it was very far from truly random. Like it was very biased around certain points, and there'd be collision. The collision as in choosing the same prime number. And this was by paper. This was put up in some paper by Diffie and someone else. I don't remember his name. Another example is where I get lazy in a different way. So, I think, okay, you know what? Prime number generation is very expensive. I'll just take two different values of E. So one guy comes and says, okay, you know what? I will take E1 as 65537 and he like I'll take E1 as E2 as 5 and N is equals to PQ. So this thing and then and then the way someone else sends this guy a message is they send C1 is just M to the power E1 mod N and C2 is just M to the power EQ mod N.
Why is he sending the same message twice?
I don't contrived scenario. But yes, I mean, for whatever reason, we're just doing maths at this point. Where might you have this? I'm not exactly sure, but assuming this is happening. So, what can an eavesdropper see? An eavesdropper can see, eavesdropper can't see E. Eavesdropper can see N, E1, E2, C1, C2. Is there any way for the eavesdropper to now figure out M? Again, you would need maths from last week. I'll do this and I'll do one faster type after this. Okay. No, the message is the same. Okay, and if they do, he will get M of E1 plus E2.
Then you have you can write an equation in terms of E1 and then you can write an equation in terms of E2.
Okay, so let's go about it. So you have M to the power E1 plus E2 mod N. Now what would you do? So in this case, this is going to be N to the power 6, 5, 5, 4, 2 mod N. Also, while we do look at the specific values of E1 and E2 I have given here, that is important. Anyone has any guesses? All the number theory people, the number theory people should be able to immediately see something here. I'll give everyone a minute to think about something and then I'll come back.
Somewhere if you use LCM, that LCM of C1 and C2 will be M raised to E1 and then take that to
So LCM of C1 and C2 would be
M e raised to
first of all, how do you take LCM?
Oh,
You're
how
considering
modern.
LCM as integers, but there might be no relations because this wraps around by n so many times. So like you can't even say that LCM of these two would be M raised to E1 anymore. Like had this mod n not been there, then LCM of C1 C2 would have been M raised to E1. A, that's not giving us any new info, and B, because of the mod n we can't even guarantee that. Okay, I'll give a hint. What's the GCD between of E1 and E2? 1. Yeah. Now there is something Nilabha covered last time. Yes, and what does Bizout say?
A E1 plus B E2 would be 1.
Such that A E1 plus B E2 is equals to 1, right? And A B can be easily computed using the extended Euclidean algorithms. You run the Euclidean algorithm, then put it back in reverse, and you can efficiently calculate A and B. It's easy to calculate. This is not a hard problem. So say you find such an A and B now. What you can do is raise C1 to the power A, multiply that by C2 to the power B. In modern, what do we get? We get m to the power E1 to the power A times m to the power E2, m to the power E2 to the power B, which is nothing but m to the power E1A plus E2B, but E1A plus E2B is equals to 1 over the integers itself. So this is nothing but m mod n. You have written the message. So you can raise something to a negative power, right? So what does it mean to raise something to negative power? It means like taking the inverse of it.
Is it easy to take an inverse mod n?
It's easy to take an inverse.
Mod n.
Mod n minus 2.
N is huge, right?
Yeah, so how do you take an, yeah, it's easy to still take an inverse. So as Nilabha mentioned, the way you take an inverse is that, you write the whole, you do the whole extended Euclidean algorithm procedures and you read the coefficient. So in particular,
Okay, we do that for
if I want to compute
E and N.
A inverse mod n, so for the inverse to exist, GCD of A and n must be 1. So there exists some x and y such that xa plus yn is equals to 1. Now when you take mod n of both the sides, you basically get xa is equals to 1 mod n because n is equals to 0. So basically A is your x is your inverse. X is your A inverse. So it's easy to get inverses mod n. Thanks for asking. Yeah. And for the last kind of an attack, and this is something called Hastad's broadcast attack. So what happens over is something cuter, in a sense. Let me try to recollect exactly what happens. Yeah. Okay. So, yes. So, this is a scary one. So, say, I want to receive messages from multiple people, okay? And so, this is an example of why small exponents are bad. So, in this case, I'm going to take like e is equals to 3. Yeah. So finding cube roots is difficult. Assume finding cube roots modulo n is difficult. Just take that for now. Yeah. Finding cube roots itself of an integer is not difficult, but finding cube root modulo n is difficult. Let's assume that. Even another assumption, and we'll break things. So say I generate 3 moduli n1, n2, n3. So these are the 3 semi-primes. Okay. And someone.
And they're all co-prime, right?
I'll come to that. So if they're not co-prime, it's trivially broken, but I'll just come to that. So say someone, okay, so let me put it this way. So E is equals to 3. These are 3 different people. Okay, these are 3 different people. This is not me. Okay, so this is Alice, this is Bob, and this is Karen. Let's just say all of them have the same value of E, but their own moduli. Okay, and I Nilabha want to send a message to them. Okay, now I'm not the one receiving messages. So what I'll do, I'll take a message and I will raise it to the power 3 mod n1, right? And I'll send this to Alice.
Sending the same message to everyone.
Yeah, I want to broadcast the message in a
Okay.
sense. Yeah, so I want to send the same message to everyone. It's some public announcement of who's the new MNP manager. Yeah, and if it's a public announcement, I might be willing to like just not encrypt it, but say it's a public, it's an announcement of who the next MNP manager actually is, and I have some secret info, and I only want my trusted friends here to know and no one else to know. So I would want to encrypt and send it to them. So I encrypt the same message. So I encrypt the exact same name 3 times, and I just send it to 3 different people using their moduli. This is normal stuff. Right? There's no abnormal behavior here. N1, N2, N3 are like taking just secure semi-primes and everything. But turns out this is bad. So first of all, if any of them share a common moduli, we are already screwed, right? Just take the GCD and you're done. So we'll assume that each of them are pairwise co-prime. Yeah. N1, N2, N3. Assume that they are pairwise coprime. So yeah, pairwise the GCD is 1, so that attack doesn't work. Turns out, what an Eve read, what an eavesdropper can see E equals to 3, N1, N2, N3, C1, C2, C3. Right? So there's an attack called Hastad's broadcast attack, and that attack attacks this whole thing in the recovery set. So does anyone want to take a shot at what might be something we use in this attack? This is something you studied today.
You can discuss this outside. We need to vacate right now.
Oh, we need to vacate now.
Yeah.
Great. Okay. So in that case, this is an excellent leading point. So this is something you all can think about. It uses something we covered today. It's called Hastad's broadcast attack, and if you look at the Hfvl notebook, it has been implemented there. Right? So the solution is also there. Another question which I will leave you with is that, say I have an RSA encryption, and so I have an RSA encrypted ciphertext, and I have the public parameters, and I cannot factor in, right? I have an oracle which does the following. For any message I send it decrypts the message using whatever key was used. It looks at the last bit, any ciphertext I send it decrypts it. It looks at the last bit of the corresponding plain text and returns that to me. Okay, so this is a very contrived example, but assume you can do it. Assume you have an oracle that does that. So oracle is this magic person. So I send my ciphertext to it. The oracle decrypts it, finds the last bit, and only sends the last bit to me. Okay, so we are assuming everything is happening under one public-private key pairs. So I can keep sending it as many ciphertexts as I want. Yeah. So given a particular message whose encryption I know, so I know the encryption, is it possible for me to recover the whole original message using this parity oracle? Turns out you can, and think about it, and again, if you want the solution, that's there in the Hfvl notebook. Yeah, with that, I think we can end the talk.